All right, so we're gonna cover um, section 6.1, and I'm also gonna go over 6.2 and upload those for you because I'm not gonna be able to be with you tomorrow. So 6.1 is vector fields. A lot of this you're gonna get when you look at the PDF that I'll put up. You'll be able to see it a lot better. You can also see that for a lot of chapter 6, I really pulled from the textbook things that, I feel you should read yourselves. Obviously, I did not pull the entirety uh, of the lesson, but a lot of them you just kind of have to read through things. So the first example here says finding a vector associated with a given point. If we let f of x, y be 2y squared plus x minus 4, that whole quantity with the I vector plus cosine x j vector be a vector field in R squared. And note that this is an example of a continuous vector field since both component functions are continuous. The vector is associated with the point 0, -1. So what we want to do is we're going to substitute the point values of x and y into the field point. So f 0, -1 is just going to be 2 -1 squared plus 0 minus 4i plus cosine 0j. So if you work your algebra out, you're just going to end up with -2i plus j. So your homework that follows that type should be pretty straightforward. Okay. All right, again, you can see that I pulled out a section from your textbook. Just as a crazy side note, I realized that next week we have a short week as well. So, in case you don't look at the PDF, you guys can also just pause the video. This one you can see in full, so you wouldn't have to wait for the PDF if you wanted to write it down. All right. Drawing a radial vector field, sketch the vector field for fxy as being x over 2i plus y over 2j. Says to sketch the vector field, choose a sample of points from each quadrant and compute the corresponding vector. The following table gives a representative sample of the points in the plane and the corresponding vectors. So what I'm going to try to do is show you the vector fields. Now, and I wonder why this says it can be. Ah, that's right. So A shows the vector field. To see that each vector is perpendicular to the corresponding circle in B, shows circles overlain on the vector field. So what I'm going to try to do is I'm going to give you the points, and then you'll be able to plug those in, and you'll be able to see how they got their vector field. So the points they used were, they made a chart. I don't think I'll be able to squeeze the chart in here, but they did 1, 0, 0, 1, -1, 0, and 0, -1, which is probably something we all would have naturally picked, right? And then they plug them in. So I'll try to get you as much of this as I can. So 1/2, comma, 0, 0, comma, 1/2, -1/2, comma, 0, and 0, -1/2. And then, so they did 4 more columns. I'm gonna try to like spread it out all over the place here so we have room, or I guess wherever we have room. And then 2, 0, 0, 2, -2, 0, and 0, -2. So then they had XY again, and that gave them 1, 0, oops, 0, 1. All right, so I do apologize if that goes into the vector field too for you, or B, but that's how they got all of this. And then again, remember that oop, did it go away? I don't know. Maybe it went away. Hopefully it did. So A shows the vector field. Well, if you guys didn't believe I was dyslexic before, right? Okay. So then what B shows circles overlaying on the vector field. So that you can see each vector is perpendicular to the corresponding circle. Okay. All right. So this is saying sketch the vector field if fxy equals the vector y minus x. So we want to create a table using a representative sample of points in a plane and the corresponding vectors. So, and then it's going to show us the vector fields. And there's an analysis that you can read when you have the PDF. So let me get you the points first, and then I'm going to try to squeeze everything on like I did before. So it's going to be And normally all 6 of these would be together, like in columns, but I can't squeeze it on there like that. So, kind of doing the best I can for you. Yeah. Let's look at this. So it tells you down at the bottom, if you can see this, A visual is a visual representation of the vector field. B is the vector field with circles centered at the origin, and C is the vector field and perpendicular to radial vector AB at point AB. Just so you can see like a different idea of stuff. Again, hopefully you see that on the PDF a little bit better than you do on the video. Yeah. All right, so it says sketching a vector field. Sketch the vector field and gives you the field. And again, we're just going to use the same, 4, 8, 12 points to find your vector fields, and you sketch them. All right, so it says to visualize this vector field, first note that the dot product of f a b dot a I, excuse me, plus b j is 0 for any point AB. Therefore, each vector is tangent to the circle on which it is located. Also, as AB approaches 0, 0, the magnitude for the vector field goes to infinity. So, to get an idea of that, it's AB approaches 0, 0, then the magnitude approaches infinity. So you can see that because the magnitude, I really don't know if I'm going to be able to squeeze all this in. The magnitude you would get by doing the square root of 1 over a squared plus b squared, really. That's what it works out to be. Okay, so that's 1. Since 1 over a squared plus b squared approaches infinity as ab approaches 0, 0, then the magnitude of the vector field approaches infinity as AB approaches infinity. So that's just explaining how that worked out. This vector field looks similar to the vector field in example 2. Okay. But in this case, the magnitudes of the vectors close to the origin are large. The table shows a sample of points and the corresponding vectors. And figure 6.6 shows the vector field. Note that this vector field models the whirlpool motion of the river. And figure 6.2b, the domain of the vector field is all of R2 except for the point 0, 0. So it's not going to be present there. All right, so let me try to squeeze in these points for you. Maybe I can get most of them in the one row column, sorry. And then you guys know to make the many columns. So those are all your points. Sorry that I can't get them to fit in the nice columns that they should be in. But that's what it looks like. And, since it's a pre-recording, you can pause it whenever you need to. All right. Next one says velocity field of a fluid. Suppose that vector xy is the following. Is the velocity field of a fluid. How fast is the fluid moving at point 1, -1? Assume that the units of speed are meters per second. So again, very similar to example 1. It's basically like 6.1 applied. So you're going to basically find V1, -1, should be 2, -1. Sorry, that's the negative for this one's out front. And that's going to be 1 squared plus -1 squared I plus 2 times 1 over 1 squared plus -1 squared. And if you work everything out, you end up getting I plus J. The speed of the fluid, so then what you would have to say is the speed of the fluid at 1, -1 is the magnitude nope, didn't spell that one right. Magnitude. Words, my friends, words of this vector. Therefore, the speed is I plus J, which is equal to the square root of 2 meters per second. So that's like the overall answer is the square root of 2 meters per second. But I guess it's better to write it as a sentence. Okay. Example 6.6 says that the vector field following is a unit vector field. Oh, show that it is a unit vector field. So what that means is that we have to show that the magnitude of each vector is 1. So that means that we're gonna have y over the square root of x squared plus y squared plus -x over the square root of x squared plus y squared. So That'll be y squared over x squared plus y squared plus x squared over x squared plus y squared, which is just going to end up being x squared plus y squared over x squared plus y squared, which is the square root of 1, which is 1. So, therefore, f is a unit vector field. Field. I gotta get the field in there. This is a solid F. Okay. All right, we got a couple of notes. Write them down. Okay. All right. So we want to sketch a vector field in 3 dimensions. So describe the vector field x, y, z as being 1, 1, z. So since object 1 is located at the origin, the distance between the objects is given by highlight. That's slide 11. Give me 1 second. All right, guys, sorry about that. I somehow just skipped this whole problem when I was preparing my lesson. So, for this vector field, the x and y components are constant. So every point in R3 has an associated vector with x and y components equal to 1. To visualize the vector f, we consider what the field looks like in the plane, in the xy plane. So in the xy plane, then z would be equal to 0. So literally each point would be a, b, comma, 0, which would have the vector of associated with it being 1, 1, 0. For points not in the xy plane, but slightly above it, the associated vector has a small but positive z component, and therefore the associated vector points slightly upward. For points that are far above the xy plane, the z component is larger. So the vector is almost vertical, and that is what this vector field shows. Oh, that's what I did. I just gave you the full explanation instead of putting it on my teacher notes. But that's fine. So you can see it now written out on the PDF. Okay. So now on to slide 11. Says describing a gravitational vector field. Newton's law of gravitation states that the vector force F equals negative g. Oh, you can see it there, where g is the universal gravitational constant. It describes the gravitational field exerted by an object, object 1 of mass 1, located at the origin on another object, object 2 of mass 2, located at a point x, y, z. Field vector denotes the gravitational force that object 1 exerts on object 2. R is the distance between the two objects, and r hat indicates the unit vector from the first object to the second. The minus sign shows that the gravitational force attracts toward the origin. That is, the force of object 1 is attractive. Sketch the vector field associated with this equation. So, since object 1 is located at the origin, object 1 at origin. The distance between the two objects is given by r equals the square root of x squared plus y squared plus z squared. The unit vector from object 1 to object 2, or hat, would be x, y, z over the magnitude. So then that would become therefore the gravitational vector field exerted by object 1 on object 2 would be this is an example of the radial vector field in R cubed. Figure 6.8 shows this gravitational field looks like for a large mass at the origin. Note that the magnitudes of the vector fields increase as the vectors get closer to the origin. Okay. Let you guys copy that down. Okay. Let's keep it rolling. Almost done. All right, so we have another definition here. We actually have a few things to highlight here. Okay. Like I said, you guys can look at a lot of this on the PDF, which I will put up for you soon, as soon as I'm done. So it says use technology to plot the gradient vector field, and it gives it to you. So use Mathematica. It's free on Google. Well, the internet. Okay, so here's your overall answer, and that's what Mathematica would have given you. So there you have it there. All right. So it says verifying a potential function. If we're given the following, a potential function for the vector field, okay, is it? So to do that, to confirm, we would need to do delta f equal to big F. So we would have f of x, or f partial, so 2 x, y, z minus y cosine x, y. Oh, sorry. Literally x, y. Ah, when I want the comma, I never put it in there, and when I don't want the comma, I keep wanting to do it. then we have f sub y. That's going to be x squared y. Nope, x squared z, sorry, so sorry. Z minus x cosine xy. Then we have fz. Therefore, and f is a potential function for f. Okay? All right. This is another situation where I'm just giving you the answer because it was just a lot easier to do it that way. All right, so it says verifying a potential function. The velocity is a fluid. Of a fluid is modeled by the following field. Verify that fxy is a potential for v. So it says to show that f is a potential, we must show delta f equal to v. Note that f of x, f little x is equal to xy, and f little y is equal to x squared over 2 minus y. Therefore, you have the following, and it is a potential function. Okay. So we have a theorem. We have two theorems. The proofs are in your textbook, so do read them if you are interested. So here's the first theorem. Let's see this whole part. Is it, important? Okay. All right. Last two examples. Showing a vector field is not conservative. Show that the rotational vector field is not conservative. So if we let P of xy equal y and Q of xy equal negative x, if f is conservative, then the cross partials would be equal. That is P sub y would equal Q sub x. Therefore, to show that f is not conservative. Check that p sub y not equal to q sub x, since p sub y equals 1 and q sub x equals -1, the vector, nope, almost again, guys, vector field is not conservative. Okay. All right, last example for this one, and then I'll save it, upload it, do all the stuff, and then I'll jump into 6.2. Showing a vector field is not conservative is the following conservative. So same kind of setup. We're gonna let P, X, Y, Z equal to 7. Q, X, Y, Z equal to -2. And R, X, Y, Z equal to X cubed. So again, if it is conservative, so if F is conservative, then we would have to have a bunch of things happen, okay? So then we would need P sub Y equal to Q sub X. Q sub Z would have to equal R sub Y, and R sub X would have to equal P sub Z. Note that means P sub Y has to equal Q sub X has to equal R sub Y has to equal Q sub Z has to equal 0. So the first two necessary equalities hold. However, so that means this one and this one hold. However, Rx equals 3x squared and PZ equals 0. So then, oh wait, sorry, it's this one and this one hold. So then Rx is not equal to PZ. Therefore, okay. All right, so I'm going to save these for you guys, and I will see you in the next video.